So let us take up a question, and the question is find the value of root 3 plus root 2 plus 1 to the power 6 plus root 3 plus root 2 minus 1 to the power 6 plus root 3 minus root 2 plus 1 to the power 6 plus minus root 3 plus root 2 plus 1 to the power 6 and the fractional part of this entire value or number. So where these brackets, they represent fractional part function. Now we need to find the fractional part of this given number. Now what I'll do is I'll write this as root 3 plus root 2 and then plus 1 to the power 6, and here I'll write root 3 plus root 2 minus 1 to the power 6. Here it is root 3 minus root 2 plus 1 to the power 6, and here I'll take minus 1 common, so minus 1 to the power 6 will be simply plus 1. So I'm going to write it as root 3 minus root 2 and minus 1 to the power 6. Now if I write the series summation for this one, so using binomial, so I'll consider this as A and this as B. So I can write the series as summation R varies from 0 to 6 nCn-r root 3 plus root 2 to the power 6 minus r, and then 1 to the power r will be same 1. So here r varies from 0 to 6 and here will be 6cr, it will be root 3 plus root 2 to the power 6 minus r and then minus 1 to the power r. In the same way, I'll write it for this one. So it will be summation r varies from 0 to 6, 6cr root 3 minus root 2 to the power 6 minus r. And for this one, it will be summation r varies from 0 to 6, 6cr root 3 minus root 2, 6 minus r, and then minus 1 to the power r. Now, if I look at these two terms, it is nothing but a plus b and a minus b. So what will happen is when this r is an odd number, in that case, these two terms they'll cancel, and when r is an even number, they'll add up, right? So what I'll do is I'll write it as 2 times and summation. Now r will take only even values, so r will be either 0, 2, 4 and 6. So I'll write it as 6cr root 3 plus root 2 to the power 6 minus r. So when the value of r is odd, these terms they'll cancel out, and when r is even, they're going to add up, right? In the same way, I can write it for second one also. There'll be 2 times and summation. Again, r will take even values 0, 2, 4 and 6, and here will be 6cr root 3 minus root 2 to the power 6 minus r. Now I'll take the two summations together. So I'll write it as 2 times and then summation r varies from 0 to 4 and 6, and I'll also take 6cr common. Then I'll write it as root 3 plus root 2 to the power 6 minus r plus root 3 minus root 2 to the power 6 minus r. When r is even, then 6 minus r will also be even, and this again is of the form a plus b and a minus b. So in this case again, all the even number terms they'll cancel. So here what I'll get is 2 times summation r varies from 0 to 4 and 6 and will be 6cr, and here I'll get 2 times. So I'll get this first term which is 6cr 6 minus r c0 root 3 to the power 6 minus r root 2 to the power 0 and then plus 6c2 root 3 to the power 6 minus r minus 2 root 2 square, and this series will continue. Now when I look at this series, root 3 to the power 6 minus r is an even number, so 6 minus r is even, 6 minus r minus 2 is even, root 2 to the power 0 is even, power 2 is even, power 4 is even. So every time when I'm getting a square root, I'm getting it with an even power. So when I'm getting square roots with even power, I know there will be no irrational terms in this expression. All the terms, they'll be simply integral. So that is the value of this number, or this number is actually an integer. Now when this number is an integer, and if I have to take the fractional part of any integer, so fractional part of any integer is simply 0. So answer to this question is 0.
Let ABC be sides of a triangle ABC which are opposite to the angles AB and C respectively. Now we are given two series, one which is S, and that is nCr b to the power n minus r c to the power r cos rb minus n minus rc, and then another series T which is summation r varies from 0 to n nCr b to the power n minus r c to the power r sine RB minus N minus RC. Now, when I look at these two series, these coefficients, they are same. And here I see cos theta and here I see sin theta. So what I'll actually do is, I'll write it as S plus iota t. Then if I'll take this summation, I can write this summation as summation r varies from 0 to n, nCr b to the power n minus r into c to the power r, and then it'll be cos rb minus n minus rc plus iota sin rb minus n minus rc. Now Euler's formula says cos theta plus iota sin theta is e to the power iota theta. So I can write it as s plus iota t will be summation r varies from 0 to n, nCr b to the power n minus r into c to the power r, and here I'll write e to the power iota rb minus n minus rc. So I can also write it as r varies from 0 to n, nCr b to the power n minus r, c to the power r, and here I'll split this term in two parts, e to the power iota rb and then e to the power minus iota n minus rc. So I'll take these terms having this power n minus r together and I'll have these terms together. So I can actually write it as summation r varies from 0 to n, nCr b into e to the power iota c to the power n minus r, and then c into e to the power iota b to the power r. Now if I look at this series, it is nCr a to the power n minus r into b to the power r, which is nothing but binomial expansion of a plus b to the power n. So I can write this series as, so it will be b into e to the power minus iota c plus c into e to the power iota b to the power n. So I'll write b cos c minus iota b sin c, and here I'll write c cos b plus iota c sin b to the power n. Now I'll take the real part together. So it is b cos c plus c cos b, and then I'll take minus iota common. So there will be b sin c minus c sin b whole to the power n. Now in a triangle ABC, we know this result that b cos c plus c cos a is a. So that's your projection formula. And then we also know that sin c upon c is equal to sin b upon b, so which is sine rule. And in this case, b sin c minus c sin b will be simply 0. So this result will be equal to a to the power n. Now I'll compare the real and imaginary part. So if I'll compare the real part, I'll get the value of s as a to the power n, and if I'll compare the imaginary part, I'll get the value of t as 0. So the sum of first series is a to the power n and the sum of second series is 0. The question is, find the sum of the series summation r varies from 0 to n minus 1 to the power r nCr upon r plus 2 cr. So first I'll simplify this expression I can write it as nCr upon r plus 2 cr. So there will be factorial n, factorial r, factorial n minus r, and here I'll write it as r plus 2 factorial upon factorial r factorial 2. So I'll cancel this factorial r with factorial r, and then I'll write it as factorial n into factorial 2, and here I'll write factorial r plus 2 and factorial n minus r. Now since r got changed to r plus 2, I have to change this n to n plus 2. So what I'll do is, I'll multiply and divide it with n plus 1 into n plus 2. So now I can write it as 2 upon n plus 1 into n plus 2, and here will be factorial n plus 2 upon r plus 2 and then n minus r, which is actually 2 upon n plus 1, n plus 2, and then it will be n plus 2 c r plus 2. Now I'll find this sum. So this sum will be, so I'll take this 2 upon n plus 1, n plus 2, and then the series sum, which is from r, that is r varies from 0 to n, minus 1 to the power r, and here it will be n plus 2 r plus 2. Now it is alternate plus minus sign, and it is sum of all the coefficients starting from n plus 2 c2 to n plus 2 c n plus 2. So what I'll do is I'll complete the series. I'll add two terms. I'll add n plus 2 c0 and then minus n plus 2 c1, and if I have added them I have to subtract them also. So n minus 2 c0 and plus n plus 2 c1. So now I can write this summation as, so this is 2 n plus 1 n plus 2. So I'll write summation. Now I'll change the variable because I've changed it from 0 to n plus 2. So I'll simply write r varies from 0 to n plus 2 and then minus 1 to the power r n plus 2 cr, and then I'll have this term which is minus 1 and then plus nc2 c1 is simply n plus 2. Now this summation c0 minus c1 plus c2 minus c3 up to n, the value of this summation is simply 0. So I'll write it as 2 upon n plus 1 n plus 2 into, it will be n plus 1. So n plus 1 will cancel. So I'll get this result as 2 upon n plus 2. So answer to this question is 2 upon n plus 2. Here the question is, if k and n are positive integers and if sk equals 1 to the power k plus 2 to the power k plus 3 to the power k plus n to the power k, then we need to find this summation r varies from 1 to m plus 1 cr sr. Now if I look at this summation, then I write summation r varies from 1 to m and it will be m plus 1 cr, and then I'll write 1 to the power r, 2 to the power r plus 3 to the power r, and it'll go all the way up to n to the power r. So now I'll separate all these summations. So I'll write summation r varies from 1 to m plus 1 cr into 1 to the power r, summation r varies from 1 to m plus 1 cr, 2 to the power r, 2 to the power r, and then it'll go all the way up to summation r varies from 1 to m plus 1 cr, and then n to the power r. Now this summation is similar to the summation which is 1 plus x to the power n, and that is summation r varies from 0 to n and then ncr x to the power of r. Now here I have two problems. One, this summation always starts from r equals 0, and here we have r equals to 1 for all the terms. And also this summation, in order to complete the series, should go all the way up to n. So in order to add this term r equals to 0, so which will be nc0 x to the power 0, which is simply 1. So I'll add 1 to every term. So this is plus 1, and plus 1. And since I have added plus 1 to each of these from 1 to n, so I have to subtract this n. So it'll be minus n. And then I'll have to also add this term which is n, which in this case will be m plus 1th term. So in the first case, it'll be, I'll need to add m plus 1, c m plus 1, 1 to the power of m plus 1, and then m plus 1, c m plus 1, 2 to the power of m plus 1, and go all the way up to m plus 1, c m plus 1, and it'll be n to the power of m plus 1. So I'll need to subtract these terms here also. Now nCn is 1. So I'll simply write 1 to the power of m plus 1 plus 2 to the power of m plus 1 and all the way up to n to the power of m plus 1. So I'll write this series as summation r varies from 0 to m plus 1, m plus 1 cr, 1 to the power r, summation r varies from 0 to m plus 1, m cr, 2 to the power of r, and summation r varies from 0 to m plus 1, n cr, n to the power r, minus n, and then minus 1 to the power of m plus 1 plus 2 to the power of m plus 1 all the way up to n to the power of m plus 1. Now this is nothing but it is ncr x to the power r, and which is binomial expansion of 1 plus x to the power n. So in this case it will be simply 1 plus 1 to the power of m plus 1, 1 plus 2 to the power of m plus 1, 1 plus 3 to the power of m plus 1, and it will go all the way up to 1 plus n to the power of m plus 1, and then minus n, minus 1 to the power of m plus 1, minus 2 to the power of m plus 1, and then minus n to the power of m plus 1. So it will be 2 to the power of m plus 1 plus 3 to the power of m plus 1, and then n to the power of m plus 1 plus 1 plus n to the power of m plus 1, and minus n minus 1 to the power of m plus 1 minus 2 to the power of m plus 1, and then minus n to the power of m plus 1. Now 2 to the power of m plus 1 will get cancelled. In the same way 3, in the same way n. So I'll get 1 plus n to the power of m plus 1, and then minus n minus 1. So there'll be minus n plus 1. So answer to this series will be 1 plus n to the power of m plus 1 minus n plus 1. Here the question is, we'll need to find sum of this series, which is 2 factorial n by 2 factorial n by 2 upon factorial n c0 square minus 2c1 square plus 3c2 square plus minus 1 to the power n plus 1 cn square, where n is an even positive integer. So what we'll do is, we'll say let n equals some 2m. So we'll write this series. We'll write the series S as c0 square minus 2c1 square plus 3c2 square, and this series will continue. Now since n is 2m here, so it'll be plus sign, and then it'll be 2m plus 1 into c 2m square. Now what we'll do is, we'll use reversing technique. So we'll reverse the series. So I'll write this term first. So I'll write 2m plus 1 c0 square. Now what about the term prior to this one? So it'll be minus 2m c1 square, and it'll continue, and in the end we'll have c 2m square. So we'll add the two series. So if I'll add the two series, we'll get 2s, and then I'll get this 2m plus 2 common from each and every term. So I'll take 2m plus 2 common, and then what we are left with is c0 square minus c1 square plus c2 square, and then it continues up to c 2m square. Now we need to find the sum of this series. So what I'll do is, I'll start with the expansion of 1 minus x to the power 2m. So it'll be c0 minus c1x plus c2x square, and it continues up to c2m x to the power 2m, and I'll also write the expansion of x plus 1 to the power 2m, and that will be c0 x to the power 2m c1 x to the power 2m minus 1, and finally it will be c2m into x to the power 0. Now I'll multiply the two series. So if I'll multiply the two series, then I'll write 1 minus x squared to the power 2m, and then there'll be many terms on the right hand side, but we are interested to find the sum of this series. So I'll write c0 square minus c1 square plus c2m square, and this series, it is a coefficient of x to the power 2m. So all I need to do is I need to find coefficient of x to the power 2m from the left hand side. Now on the left hand side, I'll write its general term. So tr plus 1th term will be 2mcr minus x squared to the power r. Now coefficient of x to the power 2m, so it simply means 2r must be equals to 2m, that is the value of r is equal to m. So the coefficient of x to the power 2m on the left hand side will be 2m cm minus 1 to the power m. So answer to this series, it is 2mcm minus 1 to the power m. So I can write the answer to this series as s equals 2m plus 2 divided by 2, and then sum of this series, which is minus 1 to the power m and 2m cm. So I'll cancel this 2 here, and then I'll write m as n by 2. So I'll write s as n by 2 plus 1 minus 1 to the power n by 2, and then it'll be nc n by 2. So now this sum is s, so we can write c0 square minus 2c1 square plus 3c2 square and plus minus 1 to the power n plus 1 cn square as n plus 2 plus 1 and minus 1 to the power n by 2, and ncn by 2 I'll write it as factorial n by 2 and factorial n by 2. Now I'll take this as well as this 2 on the left hand side. So I'll write 2 times factorial n by 2 upon factorial n into c0 square minus 2c1 square plus 3c2 square plus minus 1 to the power n plus 1 cn square as minus 1 to the power n by 2 into n plus 2, and that's your option number C. The coefficient of x to the power r in the expansion of 1 plus x to the power 10, 1 plus x to the power 20 and 1 plus x to the power 30, they are AR, BR and CR. So clearly we can write AR as coefficient of x to the power r in the expansion of 1 plus x to the power 10. So it will simply be 10 CR. In the same way, BR, so it will be 20 CR, and CR, it will be 30 CR. Now we'll need to find this summation, which is summation R varies from 1 to 10 AR B10 BR minus C10 AR. So basically I'll write it as R from 1 to 10 and AR. Now AR in this case is 10 CR, B10 is 20 C10 into 20 CR minus C10, which is 30 C10 into AR, which is again 10 CR. So we can write it as summation R varies from 1 to 10 and it is 20 C10, and this is 10 CR into 20 CR minus 30 C10 into 10 CR whole square. Now we can also write this summation as summation r varies from 1 to 10, 20C10 into 10CR, 20CR minus summation r varies from 1 to 10, 30C10 and 10CR whole square. Now the problem is the summation starts with 1. We need to start it from 0. So what we'll do is I'll write it as summation r varies from 0 to 10, 20C10, 10CR into 20CR, and since we have added one term and that is 20C10, 10C0, 20C0 which is 1, so I need to subtract 20C10 from it. And in the same way for the second series also I'll write r varies from 0 to 10, 30C10 and this is 10CR square, and then we'll subtract 30C10, so minus and minus will be plus, so then it will be 30C10. So I'll write this series as 30C10 minus 20C10 and then plus this is 20C10 summation r varies from 0 to 10 and it is 10CR into 20CR and then minus here will be 30C10 into summation r varies from 0 to 10 and that is 10CR square. So we can write it as 30C10 minus 20C10 and then plus 20C10. Now in this series, difference of suffix is constant. So we have already done these kind of series. So we know how to solve them. So answer to this series will be 30C10 and then minus will be 30C10 into now C0 square, C1 square, Cn square. So that is 2nCn. So there'll be 20C10. So this 20C10, 30C10 will cancel. So in the end we'll get 30C10 minus 20C10. Now 30C10 it is C10 and 20C10 it is B10. So answer to this question simply will be C10 minus B10 and that's your option number D. Now let us take another question which is prove that 2 to the power k nc0 into nck minus 2 to the power k minus 1 nc1 n minus 1 c k minus 1 plus 2 to the power k minus 2 nc2 n minus 2 c k minus 2 and this series it goes up to minus 1 to the power k nck n minus k c0 and we need to prove that this is equal to nck. We can write this series as this summation r varies from 0 to k 2 to the power k minus r minus 1 to the power r ncr n minus r c k minus r. Now we'll try and simplify this expression. So we'll write it as r varies from 0 to k minus 1 to the power r 2 to the power k minus r and here will be factorial n factorial r factorial n minus r factorial n minus r factorial k minus r and then factorial n minus k. So now here factorial n minus r and n minus r it will cancel. Now this summation is in terms of r. What I see here is factorial r and factorial k minus r. So I'll multiply and divide it with factorial k and then I'll take this factorial n minus k, factorial k common which is simply nck. So I'll take this nck common and then I can write the summation as summation r varies from 0 to k minus 1 to the power r, 2 to the power k minus r, and it will be simply kcr. Now I can also write this 2 to the power k minus r as 2 to the power k into 2 to the power minus r. So I'll actually write this as nck, and I'll take this 2 to the power k out, and then I'll write this summation as summation r varies from 0 to k kcr and minus 1 by 2 to the power r. So this is nck into 2 to the power k, and this is ncr into x to the power r. It is 1 plus x to the power n. So simply it will be 1 minus 1 by 2 to the power k. So this is nck 2 to the power k, and this is 1 upon 2 to the power k. So answer to this series will be simply nck.
Now question number 42 is, if 1 plus x minus 2x squared to the power 6 is equal to a0 plus a1x plus a2x square plus a12x to the power 12, we need to find the value of a2 plus a4 plus a6 plus a12. Now we'll put x as 1, we can write a0 plus a1 plus a2 plus a12, and this value, it will be equal to 0. Now if we'll put x as minus 1, then we can write a0 minus a1 plus a2 and then plus a12. In that case, it will be simply 2 to the power 6, and 2 to the power 6 is 64. Now we'll add them. If we'll add them, we'll write 2 times a0 plus a2 plus a12, and this is 64. So that is a0 plus a2 plus a4 plus a12, and this is 32. Now we need to find sum of this series which starts from a2. So we need to find the value of a0. And how do we find a0? If we'll simply put x as 0, then we'll get 1 equals a0. So that is the value of a0 is 0. So that means the value of this series, which is a2 plus a4 plus a12, will be 32 minus 1, and that is 31. And that's your option number A. Now question number 5 is, the largest integer which is less than or equal to 2 plus root 3 to the power 4 is. Now what we'll do is, we'll express 2 plus root 3 to the power 4 as its integer part plus its fractional part. So we'll write r plus f as 2 plus root 3 to the power 4, where the value of f lies between 0 and 1. Now what we'll also do is, we'll consider another series, and which is 2 minus root 3 to the power 4. Now 2 minus root 3 is 0 point something, and 0 point something to the power 4 will always lie between 0 and 1. So this value f, it will also lie between 0 and 1. Now we'll add them together. We can write this as r plus f, and it will be 2 times 4c0 2 to the power 4 plus 4c2 2 square into 3 and plus 4c4 into 3 square. So this value, it is an integer. So we can write r plus f as, this is 2. Now 2 to the power 4 is 16. This is 6 into 12, 72, and then plus 9, which is 194. Now if we add f plus f, we can write 0 and f plus f is less than equal to 2. Now this r is an integer, this 194 is an integer, so that means this f plus f, it must also be an integer. And the only integral value possible in this interval is 1. So the value of f plus f is 1. So if we put f plus f as 1, we'll get r as 193. So the largest integer which is less than or equal to 2 plus root 3 to the power 4 is 193, and that's your option B. Find the coefficient of a to the power 10, b to the power 7, and cq in the expansion of ab plus bc plus c8 to the power 10. So if I write its general term,
then I can write it as summation factorial 10 AB to the power A1, BC to the power A2, CA to the power A3 upon factorial A1, factorial A2 and factorial A3, where the sum of A1 plus A2 plus A3 is equal to 10. Now here the variables are AB, BC and CA. So I'll need to rearrange this A to the power 10, B to the power 7 and C cube in such a way so that the sum of A1 plus A2 plus A3 should be 10. So I know that I can write it as A to the power A1 plus A3, B to the power A1 plus A2 and C to the power A2 plus A3. So I should get the condition where A1 plus A3 should be 10, A1 plus A2 it should be 7 and A2 plus A3 it should be 3. Now what I already know is A1 plus A2 plus A3 is 10. So if I'll subtract the third equation, I'll get A1. So I'll get A1 as 7. If I'll subtract the second equation, I'll get A3. I'll get A3 as 3. And if I'll subtract the first equation, I'll get A2. And I'll get A2 as 0. So I can express it as AB to the power 7, BC to the power 0, and then CA to the power 3. And you can verify it also. So that is A to the power 10, B to the power 7 and C to the power 3. So I need to find this coefficient. So the coefficient of this term will be factorial 10. Now what is the value of A1? A1 is factorial 7, A2 is factorial 0 and A3 is factorial 3. So I can write 10, 9, 8. Factorial 7 will cancel. Factorial 0 is 1 and this is 3 into 2. So there will be 3, 4. So that should be 120. So the coefficient of A to the power 10, B to the power 7, C cube should be 120. Now here the question is, we need to find coefficient of x to the power 11 in the expansion of 1 plus x squared to the power 4, 1 plus x cubed to the power 7 and 1 plus x4 to the power 12. So I'll write this product as summation R1 varies from 0 to 4, 4CR1 x squared to the power R1 into summation R2 varies from 0 to 7, 7CR2 x cubed to the power R2 and then summation R3 varies from 0 to 12, 12CR3 and x to the power 4R3. So for the different values of R1, R2 and R3, we can write this as 4CR1 into 7CR2 into 12CR3 into x to the power 2R1 plus 3R2 plus 4R3. Now we need to find coefficient of x to the power 11 in this expansion. So that means sum of this power, which is 2R1 plus 3R2 plus 4R3, sum of this power, it should be 11, where R1 is an integer between 0 and 4, including both of them. R2, it lies between 0 and 7. And R3, it lies between 0 and 12. Now we'll need to look at different values of R1, R2 and R3 so that this sum, it becomes 11. So we need to write values of R1, R2 and R3 so that this sum, it becomes 11. Now first we'll consider the case when R1 is 4. So when R1 is 4, I'll get 3R2 plus 4R3. Now the only values of R2 and R3 possible in this case will be R2 should be 1 and R3 should be 0. Now I'll take the second case. So next thing I'll consider is when the value of R1 is 2. When the value of R1 is 2, I'll write 3R2 plus 4R3 and it should be 7. So one possibility is when both of them, they have the value 1. So it will be when R2 is 1 and when R3 is 1. Now what if I'll take R1 as 1? So if I'll take R1 as 1, in that case, we'll get 3R2 plus 4R3 and this value, it should be 9. So in this case, it'll be 3 here and 0 here. So R2 should be 3 and R3 should be 0. And finally, I'll take the case when R1 is 0. So if R1 is 0, we'll get 3R2 plus 4R3 equals 11. So in this case, R2 should be 1 and R3 should be 2. So we have these 4 possibilities. So now we have to find coefficient of x to the power 11. So coefficient of x to the power 11, it will be, now the first case, so it is 4c4 into 7c1 into 12c0 plus, now second case, 4c2 into 7c1 into 12c1 plus this third case, which is 4c1 7c3 into 12c0 and then plus this last one, which is 4c0 into 7c1 into 12c2. So we'll find this sum, it comes out to be 1113. So answer to this question is coefficient of x to the power 11 in this expansion is 1113. Now the question says if the sixth term in the expansion of 3 by 2 plus x by 3 to the power n is numerically greatest when the value of x is 3, then we need to find sum of possible integral values of n. Now we'll use the shortcut here, and the shortcut was in the expansion of x plus a to the power n, we'll first find this value m, and which was n plus 1 upon 1 plus mod of a by x. So here we have to find the value of n. So I'll write m as n plus 1 and then 1 plus, now what's a here? A here in this case is 3 by 2 and then upon mod x, x in this case is x by 3. Now when we'll put x as 3, this value will be 1. So I'll write m as n plus 1 upon 1 plus 3 by 2. So that should be 2 times n plus 1 upon 5. Now I'll take case 1. Now first case, when m is an integer. Now if m is an integer, then there are two greatest terms, so which is tm and tm plus 1. So now it is given that the sixth term in the expansion is numerically greatest. So that means the value of either m is 6 or the value of m plus 1 is 6. So if I'll put m as 6, then I'll get 6. So I'll get 6 equals 2n plus 2 upon 5. So that is 2n plus 2 is 30. 2n is 28. That is the value of n is 14. Now the second case, when the value of m is 5. So if I'll put m as 5, I'll write 5 equals 2n plus 2 upon 5. So 2n will be 25 minus 2, 23. So n is 23 upon 2. So it's not an integral value, so I'll discard it. So when m is an integer, then one of the possible values of n is 14. Now I'll take the second case when this m
is not an integer. So if m is not an integer, then the greatest term is given by t, greatest integer function of m plus 1. So in this case, greatest integer function of m plus 1 should be equals to 6. That is, greatest integer function of m should be 5. So if greatest integer function of m is 5, then the value of m should lie between 5 and 6. I have not taken the value 5 here because we have assumed that m is not an integer. So I'll put the value of m here. So I'll write 5 and then 2n plus 2 upon 5, and this is 6. So that should be 25. 2n plus 2, 30, 23, 2n, 28, and if I'll divide by 2, so I'll get 11.5 and n, and this is 14. So from here, I'll get two values of n. So either the value of n is 12 or the value of n is 13. So in this case, we have three values of n. Either the value of n is 14 or the value of n is 12 or the value of n is 13. So there can be two scenarios. If the sixth term is the only term which is numerically greatest, then in that case, we can have only two values of n. In that case, the sum of possible integral values of n will be 12 plus 13, and that should be 25. Or we may take up the general case where sixth term, either it's the only highest term or it may have another term with the same numerical value. In that case, we'll have three values of n, and there'll be 12, 13 and 14. So in that case, its sum will be 39. So let us take up a question, and it says, find the term independent of x in the expansion of x minus 1 by x to the power 4 and x plus 1 by x to the power 3. So what I'll do is, I can write it as x minus 1 upon x, and then I'll write it as x minus 1 upon x to the power 3 and x plus 1 upon x to the power 3. So now I'll multiply them. So this is a plus b into a minus b. So I can write it as x minus 1 upon x, and here I'll write x square minus 1 upon x square to the power 3. Now if I write the general term for this series, so I'll write x minus 1 upon x will be equal to summation r varies from 0 to 3 cr x squared to the power 3 minus r minus 1 upon x squared to the power r. So it will be x minus 1 upon x, and r varies from 0 to 3 cr, and then it will be minus 1 to the power r, and there will be x to the power 6 minus 4r. Now if I look at all the powers of x, in this case, all the powers of x, they are even, and these powers of x, they'll be multiplied with either x or with either 1 upon x. So in that case, I'll always end up getting an odd number. So in this case, there is no term which is independent of x. So the term independent of x in this case will be simply 0. Now here the question is, find the coefficient of x to the power r in the expansion of x plus a to the power n minus 1, x plus a to the power n minus 2, x plus b, x plus a to the power n minus 3, x plus b square, and this series, it continues all the way up to x plus b to the power n minus 1. So this power of x plus a, it starts from n minus 1 and it goes all the way up to x plus a to the power 0. So in this expansion, there are n terms. Now in fact, it's a geometric progression whose first term is x plus a to the power n minus 1, and its common ratio is x plus b upon x plus a. So I'll find the sum of this geometric progression, and I can write it as x plus a to the power n minus 1, and then 1 minus, now what's the value of r? Value of r is x plus b upon x plus a, number of terms is n, and then 1 minus x plus b upon x plus a.
Now I can write it as x plus a to the power n minus 1, and here I'll get x plus a to the power n minus x plus b to the power n upon x plus a to the power n, and here I'll write, so here x and x will cancel, so I'll get a minus b upon x plus a. Now x plus a to the power n minus 1, so it'll cancel n minus 1 times, and then x plus a will also cancel. Then I'll get 1 upon a minus b, and then x plus a to the power n minus x plus b to the power n. Now from this series, I'll need to find coefficient of x to the power r. Now if I write general term for this series, I can write t k plus 1, and it will be nck x to the power n minus k into a to the power k. Now I need this power of x to be equal to r, so I'll write n minus k is equal to r. So that is, the value of k is n minus r. So here the coefficient of x to the power r will be 1 upon a minus b nc n minus r, and then a to the power n minus r. In the same way, it will be the same for the second expression. So in place of a, I'll have b there. So I'll write nc n minus r, and it will be b to the power n minus r. So now I know nc n minus r is same as ncr, so I'll take it common. So I'll write ncr, and it will be a to the power n minus r minus b to the power n minus r upon a minus b. Now the question says, find the coefficient of x to the power 4, y to the power 4, and z square in the expansion of 2x minus 3y plus 4z to the power 9. So I know that the general term in this case will be summation and then factorial n. Now 2x to the power a1 minus 3y to the power a2 and 4z to the power a3 upon factorial a1, factorial a2 and factorial a3, where the sum of a1 plus a2 plus a3, and it should be equals to n, which in this case is 9. Now I need the coefficient of x to the power 4, y to the power 4 and z square. So in this case, if I'll find the sum of these powers, so 4 plus 2, and which is 10, and which is unequal to 9. So that means in this expansion, there is no term x to the power 4, y to the power 4 and z square. So the coefficient of such term will be simply 0. Now here the question is, find the coefficient of x to the power 18 in x square plus 1, x square plus 4, x square plus 9 up to x square plus 100. So I can write it as x square plus 1 square, x square plus 2 square, x square plus 3 square, and we'll go all the way up to x square plus 10 square. So basically there are 10 factors in this expression. And if I'll multiply every term with every other term, I'll get a polynomial whose degree will be x square into x square into x square 10 times. So there'll be polynomial of degree x to the power 20. Now coefficient of x to the power 20 is simply 1. But in this case, we are not interested in x to the power 20. In this case, we want to work out the coefficient of x to the power 18. So x to the power 18 is x to the power 20 minus 2. So that is, out of this product of all these x square, I'll just need to leave 1 x square. So if I'm going to leave 1 x square, in that case, I'll end up getting x to the power 18. So if I multiply all these x squares except the first one, then I'll get x to the power 18. And when this x to the power 18 gets multiplied with 1 square, so I'll have my first coefficient of x to the power 18. So coefficient of x to the power 18, I can write it as 1 square. Now, if I leave this x square from the second factor, if I multiply all other x squares,
Then again, I'll get x to the power 18. And now when this x to the power 18 gets multiplied with 2 square, I'll have another coefficient. So then it'll be 2 square and it'll continue up to 10 square. So the coefficient of x to the power 18 in this expression will be 1 square plus 2 square up to 10 square, which is n plus 1 to n plus 1 whole divided by 6. So it'll be 10 into 11 and then 21 divided by 6, which is 2 into 3. So that should be 35 into 35. So 385. So the coefficient of x to the power 18 in this case will be 385. Now here the question is, if a, b, c and d are any 4 consecutive coefficients of 1 plus x to the power n, then we need to prove that a upon a plus b plus c upon c plus d is equals to 2b upon b plus c. So what I'll do is, I'll say, suppose a is nCr minus 1, b is nCr, c is nCr plus 1, and suppose d is nCr plus 2. So first I'll find a upon a plus b. So there'll be nCr minus 1 upon nCr minus 1 plus nCr. Now here I can see the property that when n is same and r differs by 1, I can write it as nCr minus 1 and then n plus 1 cr. Now I'll try and expand it. So I'll write factorial n, factorial r minus 1 and factorial n minus r plus 1. And in the denominator I can write factorial n plus 1, factorial r, factorial n minus r plus 1. So n minus r plus 1 will cancel. I'll also cancel this factorial n with n plus 1 into factorial n, and I'll also cancel r minus 1 factorial with r into factorial r. So I can write it as r upon n plus 1. So a upon a plus b is r upon n plus 1. Now what about b upon b plus c? Now from symmetry I can say, if a upon a plus b is r upon n plus 1, then b upon b plus c will be r plus 1 upon n plus 1. And following the same argument, I can also say that c upon c plus d should be r plus 2 upon n plus 1. So when I see these numbers r plus 1 and r plus 2, they are in AP. So I can simply say a upon a plus b, b upon b plus c, and c upon c plus d. These numbers, they are in arithmetic progression. And if they are in AP, then twice b upon b plus c should be equal to a upon a plus b plus c upon c plus d. So which is your first result. Now what I'll do is, I'll take these two terms and I'll find their arithmetic mean. So if I'll find their arithmetic mean will be a upon a plus b plus c upon c plus d by 2. And arithmetic mean is always greater than or equal to. Now in this case, these terms, they are not equal because we have different values of r, right? So it should be strictly greater than their geometric mean, which is under root of a upon a plus b into c upon c plus d. Now arithmetic mean of these numbers is b upon b plus c. From here I can say b upon b plus c should be greater than under root of ac upon a plus b into c plus d. So if I'll square it, I'll get my second result. The question is, if the number of distinct terms in the expansion of x plus y plus z plus 1 upon xy plus 1 upon yz plus 1 upon zx whole square is m, and that in the expansion of x plus y plus z plus 1 upon x plus 1 upon y plus 1 upon z whole square is n, then we need to find the absolute value of m minus n. Now, when I'll square this expression, I'll get terms like x square, y square, z square, 1 upon x square, y square, plus 1 upon y square, z square, 1 upon z square, x square. So each of these terms, they're distinct and unique. So I'll have these 6 terms. And then I'll have terms when two of the variables gets multiplied with each other. So in that case, the number of such pairs will be, so I have total 6 variables. So there'll be 6C2, and 6C2 is 6 into 5 divided by 2. So that is 15. So that should be 6 plus 15. Now what will happen is, in this case, if I multiply this x with 1 upon xy, I'll get 1 upon y. If I multiply this x with 1 upon xz, I'll get 1 upon z. In the same way, when this y gets multiplied with 1 upon xy, I'll get 1 upon x. And when this y gets multiplied with 1 upon yz, I'll get 1 upon z. And then in the same way, when this z gets multiplied with 1 upon yz and 1 upon zx, I'll get 1 upon x plus 1 upon y. So out of these 15 terms, there are 6 terms in which we have a duplicate. So 1 upon x and 1 upon x, they'll pair together. 1 upon y plus 1 upon y, they'll come together. And 1 upon z plus 1 upon z will come together. So in that case, the total number of terms or total number of distinct terms will be 6 plus 15 minus 3, and which is 18. So in this case, the value of m, it should be 18. Now for the second one also, first if I'll square them, I'll get x square, y square, z square, 1 upon x square, 1 upon y square, 1 upon z square. So again that should be 6. Now plus, now if I'll consider pairs of variables, again it'll be 6c2. So that should be 15 again. And then when I'll multiply this x with 1 by x, I'll get 1. When I'll multiply this y with 1 by y, I'll get 1. And when I'll multiply this z, I'll get 1. So these 3 terms which we have taken previously distinct are not actually distinct but 1. So what I need to do is, I need to subtract 3 and add 1. So that should be 19. So the value of n is 19. Now I need to find the value of m minus n. So 18 minus 19 will be simply 1. So the value of m minus n will be 1.
If the coefficients of x cube and x to the power 4 in the expansion of 1 plus ax plus bx square into 1 plus 2x to the power 18 are both 0, then find the value of a and b. Now if I'll find coefficient of x cube. Now how do I get coefficient of x cube? When x cube from 1 minus 2x to the power 18 gets multiplied with 1, I'll get x cube. When coefficient of x square from 1 plus 2x to the power 18 gets multiplied with x, then I'll get x cube. Or when coefficient of x from the second series gets multiplied with bx square, and then I'll get coefficient of x cube. So it'll be 1 into coefficient of x cube plus a into coefficient of x square plus b into coefficient of x in the expansion of 1 minus 2x to the power 18. So there'll be 1 into minus 18c3 2 to the power 3 plus a into, and it will be 18c2 into 2 square, and then plus b into minus 18c1 into 2, and it is given that the coefficient of x cube is 0. So this result will be 0. So if I'll simplify this equation, I'll get a linear equation, and there will be 17a minus b, and this is equal to 34 into 16 divided by 3. Now I'll find coefficient of x to the power 4. Now, how do I get coefficient of x to the power 4? Now, when x to the power 4 gets multiplied with 1, I'll get it. When x cube gets multiplied with ax, or when x square gets multiplied with x square, I'll get coefficient of x to the power 4. So there'll be 1 into coefficient of x to the power 4 plus a into coefficient of x cube plus b into coefficient of x square, and again it is given as 0, so it'll be 0. So I'll get the equation as 18c4 2 to the power 4 and then minus a into 18c3 into 2 to the power 3 and then finally b into 18c2 2 square, and it should be 0. So the second equation that I'll get is 32a minus 3b, and that's equals to 240. So now I have two linear equations. So if I'll solve these two equations, I'll get the value of a as 16 and I'll get the value of b as 272 divided by 3. Now here the question is, if the summation r varies from 0 to 2n ar, which is x minus 2 to the power r, is equal to the summation r varies from 0 to 2n br x minus 3 to the power r, where ak is equal to 1 for all k greater than or equal to n, then we need to show that bn is equal to 2n plus 1 cn plus 1. Now what we'll do in this question is we'll change the variable. So I'll write let x minus 3 as some y. So I can write this as summation r varies from 0 to 2n. This is ar, and x minus 2 is simply 1 plus y to the power r, and this is summation r varies from 0 to 2n, and this is br into y to the power r. Now on the right hand side we need to find bn, and bn is actually coefficient of y to the power n. So from the left hand side and from the right hand side we need to find coefficient of y to the power n. Now coefficient of y to the power n from the second series is simply bn. Now we need to find coefficient of y to the power n from the left hand side. Now from the left hand side we know that we won't get y to the power n in any power which is less than n. So that means I'll get coefficient of y to the power n from an 1 plus y to the power n, an plus 1, 1 plus y to the power n plus 1, and it goes on up to a 2n and 1 plus y to the power 2n. Now in the question it also says ak is equal to 1 for all k greater than or equal to n. So that means we need to find coefficient of y to the power n n. Now an plus 1, a 2n, they are all 1. So it will be 1 plus y to the power n, 1 plus y to the power n plus 1, 1 plus y to the power n plus 2, and then 1 plus y to the power 2n. Now coefficient of y to the power n in 1 plus y to the power n, it will be simply nCn. In the second one it will be n plus 1 cn. Third one it will be n plus 2 cn, and then finally it will be 2n cn. Now nCn is 1. So what we can do is we can write this nCn as n plus 1 cn plus 1, and then it will be n plus 1 cn, n plus 2 cn, and 2n cn. Now here we can use the property n is same and r differs by 1. So it will be n plus 2c, n plus 1. Now here again n is same and r differs by 1. So it will be n plus 3 c n plus 1, and finally this series will continue and in the end I'll get 2n plus 1 C n plus 1. So therefore we can say this Bn must be equal to 2n plus 1 C n plus 1. Another method of solving the same question can be using sum of a geometric progression. So this series, it is a geometric progression. So find the sum of GP and then we can again find coefficient of y to the power n.
Now let us take another question in multinomial theorem. And here the question is, let 2x square plus 3x plus 4 to the power 10 is equal to this summation AR into x to the power r, where r varies from 0 to 20. We need to find the value of A7 by A13. Now generally for such questions in multinomial theorem, we look at symmetry. Say for example, the question which we have previously solved, and that was x square plus x plus 1 to the power n. There we have replaced x with 1 upon x, and if we do that, we can write this as 1 upon x square plus 1 upon x plus 1 to the power n, and here it will be x square plus x plus 1 to the power n upon x to the power 2n. So this x square plus x plus 1 to the power n, it is preserved even after taking this transformation. Now in this question, if we take the transformation 1 upon x, the symmetry is not preserved. So what we'll do is, we'll replace x with 2 upon x. Now we'll replace x with 2 upon x, it'll be 2, and here it'll be 4 upon x square. Now this is 3 into 2 upon x and plus 4 whole to the power 10, and it'll be equal to this summation r varies from 0 to 20 AR, and again in place of x we'll write 2 upon x to the power r. Now here what we'll do is, we'll take 2 upon x square common. So we'll take 2 upon x square common, we'll get 2 to the power 10 upon x to the power 20, and here it'll be 4 plus 3x plus 2x squared to the power 10, and it'll be equal to this summation r varies from 0 to 20 AR into 2 upon x to the power r. Now what we'll do is, we'll take this x to the power 20 on the right hand side, and we can write this 4 plus 3x plus 2x squared to the power 10 as this summation r varies from 0 to 20 AR x to the power r. So we'll express this as 2 to the power 10 into this summation r varies from 0 to 20 AR x to the power r, and on the right hand side we can write this as this summation r varies from 0 to 20 AR. Now we'll separate this 2 to the power r, and here it is x to the power 20 upon x to the power r. So it will be x to the power 20 minus r. Now the series on the left hand side is same as series on the right hand side. Now we need A7, which is coefficient of x to the power 7, and A13, which is again coefficient of x to the power 7 on the right hand side. So what we'll do is, we'll find coefficient of x to the power 7 from the left hand side and from the right hand side. Now from the left hand side, coefficient of x to the power 7 will be 2 to the power 10 into A7, and it'll be equal to this coefficient of x to the power 7 on the right hand side, which we'll get when the value of r is 13. So here it will be A13 into 2 to the power 13. Now we can cancel 2 to the power 10 with 2 to the power 13. We'll get 2 to the power 3 here. Now we can write this A7 upon A13 as 8, and that is the answer to this question. Now the question is, let A is nth power of this matrix 2 1 1 0, and we need to find this limit n tends to infinite A12 upon A22. Now let this matrix be B, and which is 2 1 1 0, and we'll write this as this 1 0 0 1 plus 1 1 1 minus 1. So this is I, and this is suppose C. So we can write this B as I plus C.
So now we have this matrix C, which is 1, 1, 1, minus 1. Now we find C square will be 1, 1, 1 minus 1, and then 1, 1, 1 minus 1. Now we multiply. We'll get this as 2. Now this is 0. This is 0. And then it'll be 2. So C square is basically 2i. So once we have this expression, then we know that C square will be equal to 2i. And if we multiply it with C, we'll get C cube as 2c. Now we multiply it again with C, we'll get C to the power 4 as 2c square, and 2c square is 2i. So there'll be 4i. C to the power 5, there'll be again 4c, and this sequence will continue like that. Now we have assumed this b is I plus c. Now we take nth power of b, then it will be I plus c to the power n. Now we can write this as b to the power n equals nc0 into I plus nc1 into c, nc2 into c square, nc3 into c cube, and this series will continue up to ncn into c to the power n. Now for even powers of c, it will be simply 2i, nc4 will be nc4 into 4i. So we can write this as nc0 plus 2 into nc2 plus 4 into nc4 into I, and then plus, now this is c. Now c cube is 2c, c to the power 5 is 4c. So we can write this as nc1 plus 2 into nc3 plus 4 into nc5, and it will be multiplied with c. Now we need to find sum of these two series. So this is our first series and this is our second series. Now say this is P and this is Q. Now we consider the expansion of 1 plus root 2 to the power n. It will be nc0 plus nc1 into root 2, nc2 into root 2 square, nc3 into 2 root 2. Now if we consider these terms, this is nothing but p. So it will be this p, and then if we take root 2 common, then it will be q. So we can write this as p plus root 2q. So value of p plus root 2q will be simply 1 plus root 2 to the power n. And if we take 1 minus root 2, it will be alternate plus minus. Then we'll get p minus root 2q, and there will be 1 minus root 2 to the power n. Now if we add them, we'll get the value of p. So we'll get this p as 1 by 2 into 1 plus root 2 to the power n plus 1 minus root 2 to the power n, and if we subtract them, we'll get this q as 1 upon 2 root 2, and then it'll be 1 plus root 2 to the power n minus 1 minus root 2 to the power n. So now we have worked out values of p and q. So basically we can write a, which is b to the power n, and there will be pi plus qc. So this a will be this pi, so it will be p0, 0 and p plus q into c. Now c was 1, 1, 1 minus 1. So there will be q, q, qn minus q. So this a will be p plus q, and this is q, this is q and this is p minus q. Now it says we need to find this limit n tends to infinite a12. Now a12 is first row second column, which is this q, upon a22, and a22 is p minus q. And it's given that this is equal to L. Now this is limit n tends to infinite. Now q is 1 upon 2 root 2, and this is 1 plus root 2 to the power n minus 1 minus root 2 to the power n whole divided by, now p minus q, and p minus q will be 1 by 2, 1 plus root 2 to the power n plus 1 minus root 2 to the power n and minus 1 upon 2 root 2, 1 plus root 2 to the power n minus 1 minus root 2 to the power n. Now we'll divide everything with 1 plus root 2 to the power n, and then we'll write 1 minus root 2 upon 1 plus root 2 as some lambda. So we can write this as this L will be equal to this limit n tends to infinite. This is 1 upon 2 root 2, 1 minus lambda to the power n upon 1 by 2, 1 plus lambda to the power n minus 1 upon 2 root 2, 1 minus lambda to the power n. Now this lambda, it lies between 0 and 1. So lambda to the power n, as n tends to infinite, will be simply 0. So value of this limit will be 1 upon 2 root 2 upon 1 by 2 minus 1 upon 2 root 2, which is 1 upon root 2 minus 1. And if we rationalize, we can write this as root 2 plus 1. So value of L is root 2 plus 1. So value of L is root 2 plus 1. Now L square will be 2 plus 1 plus 2 root 2, which is 3 plus 2 root 2. Now we can write this 3 as under root 9, and we can write 2 root 2 as under root a. So value of a and b, they can be 8 or 9 or 9 or 8. Then the value of a plus b will be 9 plus 8, and which is 17. So answer to this question is 17.
Hello and welcome to the world of mathematics. I present my website www.mathsmerizing.com and my YouTube channel Mathsmerizing for your kind perusal. If you like them and are inspired by the possibilities, then consider subscribing and sharing it with someone you know who might benefit from it. Thank you.